The Hercules Corona Borealis Great Wall is so large that a beam of light needs about 10 billion years to cross it, nearly 3/4 of the entire age of the universe, spent travelling from one edge of a single structure to the other. It is built from galaxies and clusters of galaxies, and it is, by some measures, the largest structure astronomers have ever mapped, though as this episode will explain honestly, that claim is genuinely contested. This episode traces how we found it, and the wall before it and the one before that, a 100-year climb in scale from the solar system we call home, out through our galaxy, out through the local group, out through superclusters, until the very idea of a single largest structure starts to break down. Along the way, one question keeps returning. Is the universe at its grandest scale actually uniform, or is there a limit to how big any one thing inside it can be? By the end, we will have an answer, hedged the way honest science always is. Start with the ground beneath your feet, because everything in this story is a matter of leaving it behind, one step of scale at a time. Earth is a rocky sphere about 12,742 kilometers across, small enough that a jet aircraft could circle it in under 2 days. It orbits the Sun at an average distance of about 150 million kilometers, a distance light itself takes 8 minutes to cross. That distance has a name, the astronomical unit, and astronomers use it as their first ruler, because kilometers stop being useful almost immediately once you leave home. Widen the view only a little, and the ruler already needs replacing. The most distant human-made object, a robotic probe called Voyager 1, launched in 1977, has been travelling outward for decades and has covered something like 24 billion kilometers, roughly 160 times the distance from Earth to the Sun. And yet Voyager 1 has still not left the Sun's gravitational influence, let alone reached another star. The nearest star system to our own, a triple system called Alpha Centauri, sits about 4.2 light-years away. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers, and even at the speed of light, the fastest anything can travel, the trip would take over 4 years. Voyager 1, moving far slower than light, would need something like 70,000 years to cover that same distance. This is the first hard lesson of this episode, and it will recur at every step. Each time we widen our field of view, the units we were just using stop being adequate, and we have to reach for a bigger one. Kilometers gave way to astronomical units. Astronomical units will soon give way to light years. Light years will eventually give way to millions, and then billions of light years. The universe does not scale gently. It scales by leaps, and each leap makes the one before it looks small. To hold on to some sense of place while that happens, picture our sun the way it would actually look from far enough away, not as the source of daylight and warmth that dominates our sky, but as a single pale point of light, indistinguishable from the thousands of other pale points scattered across a dark background. From just a few light years out, our sun already looks exactly like every other star in the sky. It has no special glow, no label, nothing to mark it as the star that happens to host a small blue and green planet with people on it. That plain, unremarkable point of light is where this journey starts, and it is worth holding on to, because by the end of this episode, we will have zoomed out so far that even entire galaxies will look the same way. Small, pale, and from a great enough distance, almost impossible to tell apart from their neighbours. Our solar system itself, if we draw its boundary at the edge of the Sun's gravitational reach rather than at the last planet, is enormous by human standards and utterly insignificant by the standards we are about to adopt. Neptune, the outermost recognised planet, orbits at about 4.5 billion kilometers from the Sun, and even that is not the edge. Beyond Neptune lies the Kuiper Belt, a disk of icy debris, and beyond that astronomers infer the existence of the Oort cloud, a vast, roughly spherical shell of icy bodies that may extend out to a light-year or more from the Sun, right up to the point where the Sun's gravity finally loses its grip to the pull of neighbouring stars. If the Sun's gravitational domain is a light-year across, then in the scale we are about to build, it is a single grain of sand. That grain of sand comparison is the one to keep in your pocket for the rest of this episode. Astronomers sometimes illustrate galactic scale by imagining a single grain of sand held at arm's length against the night sky. From that distance, the grain covers roughly the area that a modest patch of galaxies would cover if you could actually see them. It sounds like a throwaway image, but it is doing real work because human intuition was built for handling distances we can walk, run or drive, not distances that take light itself tens of thousands of years to cross. Every comparison in this episode exists to buy back a little of that intuition, one borrowed unit at a time. For most of human history, none of this scale was even suspected. The night sky looked like a fixed dome of lights at a single unknown distance, and there was no instrument sensitive enough to prove otherwise. It took centuries of careful measurement, beginning with the recognition that Earth orbits the Sun rather than the reverse, and continuing through the first successful measurement of a star's distance in 1838. Using a technique called parallax, the same shift in apparent position you see when you hold up a finger and close one eye, then the other. Parallax measurements, comparing a star's position from opposite sides of Earth's orbit 6 months apart, gave astronomers their first real rulers beyond the solar system, and those rulers immediately revealed that the nearest stars were already unimaginably far away by the standards of the time. Even after distance became measurable, most 19th century astronomers still believed the Milky Way was the entire universe. There was nothing else to compare it to, no accepted evidence of anything beyond it, and the technology of the era simply could not resolve fainter, more distant light sources into anything but fuzzy smudges. That belief held for surprisingly long, and its collapse, which comes in the next chapter, would turn out to be the first of many times this story required astronomers to admit the universe was dramatically larger than they had assumed. So here is where we stand at the end of this first stage of the climb. One planet orbiting one ordinary star, itself just a pale point of light seen from any real distance inside a gravitational bubble that would fit on a grain of sand held at arm's length against a galaxy. Everything from here widens outward, and the first widening waits just past the edge of the Sun's gravity, in the galaxy that contains our star along with a few 100 billion others. The debate that ended the 19th century assumption that the Milky Way was the whole universe is remembered as the Great Debate, a formal exchange held in 1920 between two astronomers, Harlow Shapley and Heber Curtis, arguing over what those faint smudges beyond the stars actually were. Shapley argued they were relatively nearby objects within a single enormous galaxy. Curtis argued they were entire separate galaxies, island universes in their own right, simply too far away to resolve into individual stars. Neither side had decisive proof at the time. That proof arrived a few years later in 1923, when the astronomer Edwin Hubble, using the largest telescope then in existence, identified a specific type of pulsing star called a Cepheid variable inside the Andromeda smudge. Cepheid variables brighten and dim on a predictable cycle tied directly to their true brightness, which meant that once you clocked the cycle, you could calculate how far away the star had to be for it to appear as faint as it did. Hubble's calculation placed Andromeda roughly 900,000 light-years away, later revised upward to about 2.5 million light-years as measurement techniques improved. Either number was catastrophically larger than the accepted size of the Milky Way. Curtis had been right. The smudges were other galaxies, and the universe was not one structure but countless structures, scattered across a gulf of distance no one had previously imagined. With that settled, astronomers turned to mapping the galaxy we actually live inside. The Milky Way is now understood to be a barred spiral galaxy, meaning it has a dense, elongated bar of stars at its center with curved spiral arms winding outward from either end of the bar, the way pinwheel blades curve outward from a hub. The whole disk spans roughly 100,000 light-years across, though the exact edge is fuzzy, because the density of stars simply thins out gradually rather than stopping at a hard boundary. Current estimates put the total star count somewhere between 100 billion and 400 billion, a range wide enough to remind us that we still cannot count them directly. What we can do is estimate the galaxy's total mass from how fast stars orbit its center, and that measurement carries its own famous puzzle, because stars far from the center orbit faster than the visible matter alone can explain. The extra gravitational pull is attributed to dark matter, an invisible form of matter that neither emits nor absorbs light, and can currently only be detected through its gravitational effects. We will come back to dark matter later in this episode, because it turns out to be one of the main architects of every large structure we are about to discuss. Our Sun sits inside one of the Milky Way's minor spiral arms, called the Orion Arm, roughly 26,000 light-years from the galactic center, which places it a little over halfway out from the middle toward the edge of the visible disk. The Sun, and everything orbiting it, including Earth, is moving through space at roughly 220 kilometers per second as it orbits the galactic center, and yet it still takes about 230 million years to complete a single full orbit, a span of time astronomers sometimes call a galactic year. The last time our solar system was in its current position along that orbit, dinosaurs had not yet appeared on Earth. At the very centre of the galaxy, radio and infrared observations have identified a compact, extraordinarily massive object called Sagittarius, a star, now confirmed through direct imaging in 2022 to be a supermassive black hole with a mass around 4 million times that of the Sun. It anchors the orbits of the stars nearest to the galactic core the way the Sun anchors the orbits of the planets, just on a vastly larger scale. To put the galactic year in a more human unit, 230 million years ago places us in the Triassic period, before the first dinosaurs, when the continents were still locked together in the supercontinent Pangaea. Every generation of humans who has ever lived, every civilization ever built, every treaty ever signed, has occurred in a sliver of time far too thin to register against a single one of the Sun's laps around the galactic centre. Here is the motif to hold on to from the previous stage of the climb, now updated. From far enough outside the Milky Way, our Sun is not a special point of light at all. It is one pale point among 100 billion or more, scattered across a disk 100,000 light-years wide, indistinguishable in brightness or colour from countless others nearby. That is the honest picture. Not a star at the centre of anything, but one star among billions, riding a spiral arm about halfway out from a galactic centre it circles once every 230 million years. It is a strange kind of comfort, knowing exactly how ordinary our position is, and it is also the correct scientific picture, confirmed independently by star counts, orbital dynamics, and eventually by simply photographing other spiral galaxies from the outside, and recognizing the same structure looking back. But even the Milky Way, spiral arms and all, is not an isolated structure floating alone in blank space. Galaxies, it turns out, are almost never alone. They gather. And the way they gather is where the story of scale takes its next major leap, from a single galaxy to something astronomers call a group. Groups. That is the technical term for the next rung up from a single galaxy, and it is a deliberately modest word for what turns out to be a genuinely large structure. Our own group is called, without much poetry, the local group, and it currently has around 54 known member galaxies, though the true number keeps climbing as fainter, smaller companions are discovered around the edges. The local group is dominated by two big spiral galaxies, our Milky Way and the Andromeda Galaxy, the same object at the centre of the great debate from the previous chapter. A third significant spiral, the Triangulum Galaxy, sits nearby, smaller than either of the two giants but still substantial. Everything else in the group is a dwarf galaxy, some containing a few billion stars, some containing only a few 100,000 dim companions caught in the gravitational orbit of one of the larger members. Two of the Milky Way's own dwarf companions are visible to the naked eye from the southern hemisphere without any equipment at all. The Large Magellanic Cloud and the Small Magellanic Cloud, named for the navigator Ferdinand Magellan's crew, who recorded them during a 16th century voyage, though peoples in the southern hemisphere had of course observed them for millennia before that. The Large Magellanic Cloud sits about 160,000 light-years away, and the Small Magellanic Cloud about 200,000 light-years away, both close enough, on the scale we are building, to be considered practically next door. The local group as a whole spans roughly 10 million light-years across, measured from one edge of its gravitational influence to the other, which means our familiar jump from kilometers to light-years has already become insufficient in turn. Astronomers increasingly reach for an even larger practical unit here, the megaparsec, equal to roughly 3.26 million light-years, simply because writing a distance in megaparsecs is easier than writing the equivalent light-year figure over and over in a technical paper. We will keep using light-years in this episode for clarity, but it is worth knowing the shorthand exists because professional astronomy papers about the structures still ahead of us are written almost entirely in megaparsecs. The two giant spirals at the heart of the local group are not standing still relative to each other. Detailed measurements of Andromeda's motion, including its sideways drift measured by the Hubble Space Telescope over multiple years, show that it is approaching the Milky Way at roughly 110 kilometers per second. The two galaxies are on a collision course, and in around 4.5 billion years, give or take a substantial margin of error, they are expected to merge into a single, larger elliptical galaxy, a hypothetical future object astronomers have taken to nicknaming Milkomeda. This will not be a collision in the way two cars collide. Galaxies are mostly empty space between stars, So a galactic merger is really a long, slow gravitational dance, lasting hundreds of millions of years, with individual stars rearranging their orbits rather than smashing into one another. The chance of our actual Sun colliding with another star during the merger is vanishingly small. The chance of the night sky looking completely different for whoever is around to see it by then, with Andromeda spread across half the visible sky as it plunges closer, is close to certain. Some of the Milky Way's dwarf companions are not merely orbiting, they are actively being consumed. The Sagittarius dwarf spheroidal galaxy, discovered in 1994, is currently being torn apart by the Milky Way's gravity, its stars stretched into a long stream that wraps around our galaxy's poles, detectable today only because astronomers can trace the distinct chemical signatures and motions of its stars against the background of the Milky Way's own. Galactic cannibalism of this kind, small galaxies slowly shredded and absorbed by larger ones, is now understood to be one of the ordinary ways big galaxies grow. The Milky Way itself likely reached its current size in part by consuming a series of smaller galaxies over billions of years, evidence for several of which still survives as distinct streams of stars in its outer halo, discovered only in the last 2 decades through painstaking surveys of stellar motion. For a human-scale sense of what loosely bound actually means at this distance, if the local group's 10 million light-year span were shrunk down so that the distance between the Milky Way and Andromeda, about 2.5 million light-years in reality, was represented by the length of a football field, then the Sun itself, on that same scale, would be smaller than a single atom, and Earth's orbit around it would be too small to draw at all. Groups and clusters are not just big, they are big in a way that makes even entire galaxies, and the vast stellar populations inside them collapse down to essentially dimensionless points. Beyond the 2 giants and their satellite dwarfs, the rest of the local group's members drift in loosely bound orbits, some clearly gravitationally attached to the Milky Way's own extended halo, others attached to Andromeda's, and a handful sitting in a kind of gravitational no-man's land between the two, technically part of the group but not clearly tied to either giant. This structure, one modestly sized group built around 2 dominant spirals and a scattering of dwarfs, turns out to be an extremely common pattern in the universe. Galaxies overwhelmingly do not exist in isolation. The lonely, isolated galaxy with no neighbours at all is the exception, not the rule. The vast majority of galaxies, ours included, live inside some kind of group, and the vast majority of groups, in turn, live inside something larger still. That something larger is where the scale climb accelerates again. The local group itself is not floating freely through space. It sits on the outer edge of a vastly bigger structure, one containing thousands of galaxies rather than dozens, bound together not by the tight close-range gravity that holds our own group together, but by a broader gravitational pull spanning tens of millions of light-years. Astronomers call these enormous assemblies clusters, and the nearest big one to us, close enough that its gravity is measurably tugging our entire local group toward it, is where this story goes next. If the local group is a small town, the Virgo Cluster is the nearest true city, and it is close enough in cosmic terms that its gravitational pull is quietly reshaping the trajectory of everything in our neighbourhood, including us. The Virgo Cluster sits roughly 54 million light-years away in the direction of the constellation Virgo, and it contains, by current counts, somewhere between 300 and 2,000 galaxies, a number so much larger than the local group's 54 that the difference in scale from group to cluster is not incremental. It is a genuine change of category. At the heart of the Virgo Cluster sits a giant elliptical galaxy called Messier 87, or M87 for short, a galaxy so massive that some estimates put its total mass, including its diffuse halo of stars and dark matter, at several thousand times that of the Milky Way. M87 is famous for a specific reason beyond its size. In 2019, an international collaboration called the Event Horizon Telescope released the first ever direct image of a black hole's shadow, a dark circle ringed by glowing superheated gas, and the black hole they image sits at the centre of M87. That black hole has a mass roughly 6.5 billion times the mass of the Sun, more than 1,000 times larger than the one at the centre of our own galaxy, a difference in scale that mirrors the difference between our modest local group and the giant cluster surrounding M87 itself. Clusters like Virgo hold together in a way that groups like ours do not yet fully manage. A cluster's member galaxies are not just loosely drifting past one another, they orbit within a shared, deep gravitational well, one massive enough that astronomers describe the whole cluster as gravitationally bound, or virialized, meaning it has settled into something like a stable, self-contained orbit pattern, rather than still collapsing or dispersing. One striking piece of evidence for how much unseen mass a cluster like Virgo actually contains comes from the space between its galaxies, which is not empty. It is filled with an extremely thin but extremely hot gas, heated to tens of millions of degrees by the sheer gravitational energy of the cluster's collapse, and glowing not in visible light but in X-rays, detectable by orbiting X-ray telescopes. That hot intracluster gas actually contains more ordinary matter, by mass, than all the stars in all the cluster's galaxies combined, and even that gas is dwarfed by the cluster's total mass in dark matter. Inferred once again from how fast individual galaxies are orbiting within the cluster, orbits far too fast to be explained by the visible mass alone. Here is where the anomaly that first hinted at dark matter's existence actually began, decades before the term became common. In the 1930s, the astronomer Fritz Zwicky measured the velocities of galaxies within a different, more distant cluster, the Coma cluster, and found they were moving so fast that the cluster's visible mass could not possibly hold them together gravitationally. By his calculation, the cluster should have flown apart long ago. Since it clearly had not, Zwicky concluded there had to be a large quantity of unseen matter providing the missing gravity, and he gave it a name, dark matter, though his conclusion was largely ignored for nearly 40 years before later observations of individual galaxy rotation, and eventually of clusters like Virgo, confirmed he had been right all along. Our own local group, and by extension our own Milky Way, and our own Sun and our own planet, is not simply sitting near the Virgo cluster as a neutral bystander. We are quite plainly falling toward it, pulled by its gravity at a measurable rate, part of a slow, multi-billion-year infall that will likely never actually complete, because the universe's overall expansion is working against it. This tug-of-war between local gravity pulling things together and cosmic expansion pulling everything apart turns out to be the defining tension of every structure larger than a cluster, and it is the reason the next step up in scale looks nothing like a scaled-up version of a cluster. To size the Virgo cluster in a way a human mind can actually hold, light leaving M87 today would not reach Earth for 54 million years, meaning the black hole image captured in 2019 shows M87 not as it is now, but as it was roughly 54 million years ago, a time when Earth's dominant land mammals were still small, and primates had not yet split off in any form resembling what we would recognize. Every structure from here forward carries that same property, growing more pronounced with each step. We are never looking at the present. We are looking at increasingly old light, a kind of layered time capsule stacked outward in every direction, and the largest structures in this episode will turn out to be so distant that the light reaching us left when the universe itself was in its youth. Beyond the cluster, gravity has not had time to fully finish the job. What is left is something looser, stranger, and, in its own way, far more revealing about the actual architecture of the universe, the supercluster. Every structure described so far, the local group, the Virgo Cluster, exists in 3 dimensions, but for most of the 20th century, astronomers could only measure 2 of those dimensions directly. A telescope image tells you where an object sits on the sky, its position in what amounts to a flat photograph, but not how far away it actually is. Without distance, a faint nearby dwarf galaxy and a genuinely enormous but very distant galaxy can look identical, a smudge of light at a certain sky position, with no way to tell them apart. Solving that problem, filling in the missing 3rd dimension for hundreds of thousands of galaxies at once, is what finally made it possible to see structures larger than any single cluster, and the tool that did it is called redshift. Redshift works because the universe is expanding, and light travelling through expanding space is itself gently stretched along the way, shifting toward longer, redder wavelengths the farther it travels, the same way a stretched rubber band with lines drawn on it spreads those lines farther apart as the band lengthens. The effect is closely related to, though not identical to, the Doppler effect that makes an ambulance siren sound lower in pitch as it speeds away from you. Crucially, the amount of redshift in a distant galaxy's light is directly related to how far that light has travelled, and therefore how far away the galaxy is. In 1929, the astronomer Edwin Hubble, working again with Andromeda-scale distance measurements he had helped pioneer, showed that more distant galaxies consistently showed greater redshift in a roughly straight-line relationship now called Hubble's law. That relationship gave astronomers, for the first time, a practical way to estimate a galaxy's distance, just by measuring how far its light had shifted toward red, without needing to identify a rare pulsing Cepheid star inside it first. Once redshift could stand in for distance, the natural next step was obvious. Measure the redshift, and therefore the approximate distance, of not just one galaxy but tens of thousands of them, and plot every single one on a genuine three-dimensional map rather than a flat photograph. That project, called a redshift survey, began in earnest in the late 1970s with the Center for Astrophysics Redshift Survey, led by the astronomers Mark Davis, John Huchra, and Margaret Geller, working at the Harvard-Smithsonian Center for Astrophysics. Their team spent years painstakingly measuring redshifts for thousands of galaxies, one at a time, using a technique called spectroscopy, splitting each galaxy's light into its component wavelengths, the way a prism splits sunlight into a rainbow, then measuring exactly how far familiar chemical signatures within that light had shifted toward red. What that first three-dimensional map revealed, once plotted, stunned the researchers who made it. Galaxies were not scattered through space randomly, the way stars might be scattered if you shook a jar of sand. Instead, they clumped along thin, elongated structures with enormous nearly empty regions in between. In 1981, the astronomer Robert Kirshner and colleagues, examining redshift data in the direction of the constellation Bootes, found an enormous, startlingly empty region, an area roughly 330 million light-years across, containing far fewer galaxies than any surrounding patch of comparable size. The discovery was almost an accident, a gap noticed while the team was actually searching for something else, but it became one of the first confirmed cosmic voids, a name astronomers now use for any of these vast galaxy-poor regions. Then in 1989, the same Harvard-Smithsonian team, extending their original survey, identified a filament of galaxies stretching across an even larger span, a structure they named the Great Wall, which we will return to properly in the next chapter. For the first time, astronomers had direct, mapped evidence that on the largest scales, matter in the universe is arranged less like scattered sand and more like a sponge, dense along certain threads, and almost entirely absent in the spaces between them. The CFA surveys mapped a few thousand galaxies at a time, an extraordinary achievement for the era, but still a small sample compared to what came next. The 2-degree field galaxy redshift survey, completed in the early 2000s using a telescope in Australia, measured redshifts for over 220,000 galaxies. The Sloan Digital Sky Survey, begun in 2000 and still expanding its dataset today, has measured redshifts and therefore approximate three-dimensional positions for more than 1 million galaxies and several million other cosmic objects, including quasars, extraordinarily bright, distant objects powered by supermassive black holes actively feeding on surrounding gas. Each successive survey did not just add more galaxies to the map. It extended the map's reach dramatically farther out, and every time the reach extended, new structures appeared at the edge of what could be seen, each one larger than anything found before. That pattern, bigger surveys revealing bigger structures, is the pattern this entire episode is built around, and it has not yet stopped. The term supercluster is older than the precise definition astronomers now use for it. As early as the 1950s, the astronomer Gerard de Vaucouleurs proposed that the local group and the Virgo Cluster were both part of a single, much larger structure he called the local supercluster, defined simply by regions of the sky where galaxies were noticeably denser than average. That definition worked well enough for decades, but it had a real weakness. Density alone does not tell you whether a structure is actually gravitationally connected, or whether you are just looking at a chance alignment of unrelated galaxies that happen to sit along the same line of sight. In 2014, a team led by the astronomer R. Brent Tully proposed a fundamentally different way to define a supercluster, based not on where galaxies happen to sit, but on where they are actually moving. Every galaxy in the universe carries two components of motion, the overall stretching of space itself, which Hubble's law describes, and a smaller, additional motion caused by the local pull of nearby mass concentrations, called peculiar velocity. Tully's team mapped the peculiar velocities of tens of thousands of galaxies across a huge volume of space, and found that those velocities organized themselves into what looked like drainage basins, the same way rainfall on a landscape naturally flows toward the nearest river, regardless of exactly where it lands. Galaxies within a given basin were all flowing, gradually, toward the same central gravitational attractor, even if they were flowing from wildly different directions and distances. A supercluster, by this new definition, is one of those basins. every galaxy whose motion is ultimately headed toward the same shared gravitational center. Using this method, Tully's team identified the basin containing our own Milky Way, our local group, and the entire Virgo Cluster, and gave it a name drawn from Hawaiian Laniakea, meaning immense heaven, chosen partly in honor of Hawaii's role in modern astronomy through its mountaintop observatories. Laniakea spans roughly 520 million light-years across, contains an estimated 100,000 galaxies, and has a total mass estimated at around 100,000 trillion times the mass of the Sun. Within that vast basin, the Virgo Cluster, which felt so overwhelming just one chapter ago, turns out to be only a modest regional hub, not the center. The true gravitational center Laniakea's galaxies are all slowly flowing toward is a region called the Great Attractor, and the Great Attractor comes with its own strange story. Astronomers first noticed something pulling on our local group in an unexpected direction back in the late 1970s and early 1980s, when measurements of galaxy motions showed a consistent drift toward a specific patch of sky at a speed of around 600 kilometers per second, far too large to be explained by anything then catalogued in that direction. The trouble was that the direction in question sits almost directly behind the dense stars, gas, and dust of the Milky Way's own disk, a region astronomers call the zone of avoidance, because it is nearly impossible to see through in ordinary visible light. It took years of work using longer wavelengths, X-rays and infrared light, which can penetrate dust far more easily than visible light, to finally confirm what lay behind the obscuring band. A massive concentration of galaxy clusters roughly 250 million light-years away, now understood to be the Great Attractor's actual mass, though it is likely itself just a prominent local feature within an even larger, still poorly mapped, concentration of mass in that direction. The discovery of Laniakea and its Great Attractor marked a genuine shift in how astronomers describe the universe's structure. It is not merely a collection of galaxies scattered with occasional dense clumps. It is organized, at the largest gravitationally coherent scale we can currently define, into basins of flow, immense regions where billions of stars across 100,000 galaxies are almost imperceptibly slowly, sliding toward the same shared gravitational low point, the way water slides toward the same low point in a landscape no single drop of rain could ever see the shape of. And even Laniakea, a structure containing our entire galaxy as one utterly unremarkable member among 100,000 others, is not the end of the story. A 2019 study, using an expanded galaxy velocity catalogue, found tentative evidence that Laniakea's basin might connect, at its outer edges, to the flow patterns of the neighbouring Perseus-Pisces supercluster, raising the possibility that the true boundary between one gravitational basin and the next is far blurrier, and the structures involved potentially far larger, than the original 2014 map suggested. The instrument keeps getting better, the boundary keeps moving, and the next structures in this story are not even defined by gravity alone, but by something stranger, patterns baked into the universe from its very first fractions of a second, which grew over billions of years into the largest visible arrangement of matter that exists. Rewind the story of structure back to its true beginning, not to the Big Bang itself, but to a fraction of a second after it, during an extraordinarily brief period called inflation, when the universe is thought to have expanded by an almost inconceivable factor in a tiny sliver of time. During that expansion, tiny quantum fluctuations, the same kind of inherent randomness that governs particles at the smallest scales, were stretched from subatomic size up to sizes spanning what would eventually become entire galaxies and clusters. Those fluctuations left the early universe slightly lumpy, with some regions a tiny fraction denser than average, and others a tiny fraction sparser, differences so small in the cosmic microwave background, the faint afterglow of the universe's early hot phase, that they show up as variations of only about 1 part in 100,000 across the sky. That barely perceptible lumpiness is, astonishingly, the entire seed pattern for every structure described so far in this episode, and every structure still to come. Gravity, given enough time, is an amplifier. A region that starts out just slightly denser than its surroundings pulls in slightly more matter than its surroundings, which makes it slightly denser still, which lets it pull in even more. A self-reinforcing feedback loop that, given billions of years, turns a 1 part in 100,000 variation into the difference between a galaxy cluster and an empty void. But gravity does not amplify density fluctuations evenly in all directions. Matter collapsing under its own gravity naturally tends to flatten first along one axis, forming sheet-like structures, and then contract further along a second axis within that sheet, forming elongated, thread-like filaments before finally condensing at especially dense points along those filaments into the tightly bound knots we recognize as clusters. This is not a theory invented to fit the observations described in earlier chapters. It emerged first from computer simulations of gravity acting on a simulated early universe, and only afterward was confirmed to match what redshift surveys were independently finding in the real sky. The most influential of these simulations, called the Millennium Simulation, was run in 2005 by an international team using a supercomputer to track the gravitational evolution of over 10 billion simulated particles of matter standing in for dark matter and ordinary matter together across a simulated volume, roughly 2 billion light-years on a side, evolved forward through simulated cosmic time from a nearly uniform early state to a present-day state. When the simulation finished, the resulting distribution of matter looked, structurally, almost identical to what real redshift surveys like the Sloan Digital Sky Survey were mapping in the actual universe. Dense knots connected by elongated filaments, those filaments bounding enormous, nearly empty voids, and thin sheet-like walls stretched between them. Astronomers now call this overall pattern the cosmic web, and it is the organizing structure of essentially everything at scales larger than an individual galaxy cluster. Picture it the way the simulations render it, and the way real redshift maps confirm it. Not clumps floating in isolation, and not a random scatter, but something closer to a sponge, or a length of loosely knotted rope stretched across an enormous volume, glowing wherever galaxies cluster along its threads and going almost entirely dark in the cavernous spaces those threads bound. The bright threads are called filaments, ropes of galaxies and dark matter, tens to hundreds of millions of light-years long, typically only a few million light-years thick. The dark spaces between the threads are called voids, and they are anything but small. A typical void spans somewhere between 30 million and 300 million light-years across, and while voids are not perfectly empty, containing a scattering of dim, isolated galaxies, they hold only a small fraction of the galaxy density found within filaments and clusters. Where several filaments cross, gravity has had the most material to work with, and the result is one of the massive galaxy clusters described in earlier chapters, a bright node sitting at the intersection of the web's brightest threads. The scale of individual filaments and voids already dwarfs everything covered so far in this episode. Laniakea, the supercluster containing our entire galaxy and 100,000 others, spans roughly 520 million light-years, and a single cosmic void can be nearly as large. That comparison alone tells you something important. Superclusters like Laniakea are not the biggest independent objects in the universe's structure. They are simply the brightest, most gravitationally organized threads within something bigger still, the web itself, and the web's individual filaments. When you start finding the longest, most galaxy-dense ones, turn out to stretch across distances that make even Laniakea look like a single strand in a much larger weave. The next few chapters follow the hunt for exactly those longest threads, the specific filaments astronomers have identified as, for a time at least, the largest connected structures ever mapped in the observable universe. For a little over a decade, the largest connected structure known in the universe was the one discovered almost by accident in 1989. By the same Harvard-Smithsonian team, led by Margaret Geller and John Huchra, that had already mapped the Boots void and pioneered redshift surveys in general. Extending their original CFA redshift survey, with a second larger installment, they plotted the positions of thousands of additional galaxies and noticed an extended, wall-like arrangement of galaxies stretching across their survey volume, one continuous, connected filament far longer than any structure previously catalogued. They called it, plainly, the Great Wall, later distinguished from a subsequent discovery as the CFA2 Great Wall. The CFA2 Great Wall stretches roughly 500 million light-years in length, about 300 million light-years in width, and only around 16 million light-years in thickness, a genuinely sheet-like structure flattened the way the earlier chapter's discussion of gravitational collapse predicted matter would flatten before it ever formed clusters or filaments. It sits roughly 200 million light-years from Earth, close enough, on the scale of this episode, that a portion of it is visible in relatively modest amateur telescope surveys, though recognizing its true extent required the full statistical power of a redshift survey, mapping thousands of galaxies across a wide patch of sky simultaneously. At the time of its discovery, the CFA2 Great Wall was the largest structure identified in the observable universe, and it briefly became a genuine challenge to existing models of how quickly structure could form, because standard theories of gravitational collapse from a nearly smooth early universe struggled to explain a coherent structure quite that large having had enough time to assemble. That challenge was still being debated when an even larger structure turned up, this time from the Sloan Digital Sky Survey, the redshift survey introduced in an earlier chapter for its million-plus galaxy catalogue. In 2003, the astronomer J. Richard Gott III and colleagues, analysing the early Sloan data, identified a filament of galaxies stretching approximately 1.37 billion light-years in length, roughly 80% longer than the CFA2 Great Wall, and named it, following the established naming convention, the Sloan Great Wall. It sits at a distance of roughly 1 billion light-years from Earth, meaning the light astronomers used to map it left its source when the universe was already several billion years old, but Earth's solar system had not yet formed. The discovery method behind both walls is worth explaining honestly, because it is easy to hear the word wall and imagine something with a crisp, obvious boundary, the way a brick wall has an obvious edge. Real cosmic walls are identified statistically by feeding a redshift survey's full three-dimensional galaxy catalogue into an algorithm that looks for regions where galaxies form an unusually elongated, connected, overdense structure well beyond what a random distribution of the same number of galaxies would produce by chance. Different algorithms, given the same underlying data, can draw the boundary of a structure like the Sloan Great Wall slightly differently, extending it a bit further in one analysis or trimming it in another, which is part of why later chapters in this episode will describe genuine, ongoing scientific disagreement about exactly how large some of the largest claimed structures actually are. The Sloan Great Wall's core, the unambiguous, dense backbone that essentially every analysis agrees on, is real and well established. Its precise outer boundary, like the boundary of most filaments in the cosmic web, is inherently a little fuzzy, a matter of where you draw the statistical line rather than a hard physical edge. For 12 years after its 2003 discovery, the Sloan Great Wall held the title of the largest known structure in the observable universe, a genuinely impressive run, given how quickly the surveys behind it kept expanding, and how many opportunities that gave for something even larger to turn up. It was eventually surpassed, not by a bigger, sharper-edged wall found through the same method, but by a structure identified through an entirely different technique, one that did not rely on directly mapping galaxy positions at all, but instead tracked flashes of light from some of the most violent explosions in the universe. That discovery, and the debate it triggered over whether it deserved the title at all, is where the story goes next. In 2013, three astrophysicists, Istvan Horvath, John Hackler, and Zsolt Bergoli, published a paper describing an entirely different way of hunting for large-scale structure, one that did not rely on ordinary galaxies at all. Their method used gamma-ray bursts, extraordinarily energetic flashes of high-energy radiation, thought to be produced either by the catastrophic core collapse of certain very massive dying stars, or by the violent merger of two neutron stars, the collapsed remnants left behind by earlier supernovae. A single gamma-ray burst can, for a few seconds, outshine an entire galaxy, which makes it detectable across almost the entire observable universe, far beyond the distance at which most individual galaxies can be directly resolved and measured. Horvath and his colleagues plotted the sky positions and estimated distances of a set of gamma-ray bursts detected by orbiting gamma-ray observatories and found an unusual concentration. A cluster of bursts, more of them than random chance would predict, all located in roughly the same direction and roughly the same distance range toward the constellations Hercules and Corona Borealis. Based on the estimated distances of the bursts involved, they calculated that this concentration, if it represented a single connected structure the way the Sloan Great Wall does, would span somewhere in the range of 6 billion to 10 billion light-years, an almost unimaginable claim given that the entire observable universe is only about 93 billion light-years across from edge to edge. If the high end of that estimate held up, the structure they had found, which came to be called the Hercules Corona Borealis Great Wall, would be roughly 7 times larger than the Sloan Great Wall, and would represent something like 1/10 the diameter of the entire visible universe, packed into a single connected clustering of matter. That is an extraordinary claim, and it deserves the caution the actual scientific community has given it. Unlike the Sloan Great Wall, mapped from the redshifts of hundreds of thousands of individual galaxies, the Hercules Corona Borealis Great Wall is built from a sample of only a few dozen gamma-ray bursts, because gamma-ray bursts are genuinely rare events, and only a limited number have ever been detected with distance measurements precise enough to include in this kind of analysis. A structure inferred from dozens of data points carries a very different level of statistical confidence than one inferred from hundreds of thousands, and several follow-up studies since 2013 have questioned whether the apparent clustering represents a real physical structure at all, or whether it is instead a statistical artifact, the kind of chance clumping that can appear in almost any dataset small enough, especially once you factor in how gamma-ray bursts are detected in the first place, since detection depends on which parts of the sky happen to be observed by which instruments at which times, a pattern that can itself create the illusion of clustering that is not really there. This is a case where the responsible thing to do is state plainly what is settled and what is not. What is settled, a statistically notable excess of gamma-ray burst really was found clustered in that region of sky, and that distance range in the actual observed data by a peer-reviewed analysis. What is not settled, and remains actively debated among astronomers more than a decade later, is whether that excess reflects an actual physical structure, a real overdensity of matter stretching billions of light-years across, or whether it is a statistical illusion produced by a small sample size and uneven sky coverage. Some researchers have proposed that even if the excess is real, it may represent a genuine but far smaller structure than the original estimate, one closer in scale to the Sloan Great Wall rather than dramatically larger than it. Astronomers who study large-scale structure tend to treat the Hercules Corona Borealis Great Wall, today less as a confirmed record holder, and more as an open question, a genuinely interesting anomaly in the gamma-ray burst catalogue that has not yet been resolved with the kind of confidence that the more conventional, galaxy-based Great Walls enjoy. That unresolved status turns out to matter for more than just bragging rights over which structure is technically the largest. It connects directly to a much bigger theoretical question that the rest of this episode is building toward. Exactly how large is a structure allowed to be, according to our best current models of how the universe grew, before its existence starts to actually strain those models? If a genuine confirmed structure 10 billion light-years across turned up, it would not just be a curiosity. It would be a real problem for cosmology. And as it happens, the Hercules Corona Borealis Great Wall was not the last time a claimed structure of roughly that scale would raise exactly that problem. In 2021, a doctoral student named Alexia Lopez, working at the University of Central Lancashire, announced the discovery of a structure using a technique different again from either galaxy redshift surveys or gamma-ray burst clustering. Lopez studied the light from distant quasars, the extraordinarily bright cores of galaxies powered by actively feeding supermassive black holes, introduced briefly in an earlier chapter as some of the brightest objects the Sloan Digital Sky Survey catalogues. As a quasar's light travels toward Earth across billions of light-years, it passes through any intervening clouds of gas that happen to lie along the way, and those clouds imprint a very specific signature onto the quasar's light spectrum, a signature associated with a particular form of magnesium ions, which absorb light at precise well-known wavelengths. By examining the spectra of thousands of quasars and mapping every location where that magnesium absorption signature appeared, Lopez was effectively mapping the locations of gas clouds, and by extension galaxies strung out across an enormous volume of space that standard redshift surveys, which need to directly detect a galaxy's own light, could not easily reach. What emerged from that mapping was an arc-shaped alignment of absorption signatures, curving gently across a huge stretch of sky at a distance corresponding to roughly 9.2 billion light-years from Earth. Lopez named it the Giant Arc and calculated its length at approximately 3.3 billion light-years, which would make it comparable in scale to, or in some estimates larger than, the more established Sloan Great Wall, though built from an entirely different and less thoroughly tested detection method. In 2024, Lopez and colleagues announced a second structure discovered using the same quasar absorption technique, in roughly the same region of sky and at a similar distance as the Giant Arc. A ring-shaped arrangement of absorption signatures, which they named the Big Ring, estimated at approximately 1.3 billion light-years across, made distinctive not just by its size but by its unusual closed-loop shape, unlike the elongated filaments and sheets the cosmic web is generally expected to produce. Both of these findings deserve the same careful hedging as the Hercules corona Borealis Great Wall from the previous chapter, and for closely related reasons. Quasar absorption mapping is a genuinely powerful technique, but it is also newer and less independently cross-checked than direct galaxy redshift surveys. And it relies on statistical pattern recognition across a relatively limited number of quasar sightlines, which introduces real questions about how confidently a given pattern can be distinguished from a chance alignment. The big ring shape raises an additional specific concern. Standard models of structure formation, built on the gravitational collapse process described earlier in this episode, do not straightforwardly predict genuinely ring-shaped structures at this scale. A ring is not an obvious byproduct of filaments, walls, and voids forming through gravity acting on early density fluctuations, which means that if the big ring is confirmed as a real, physically connected structure, it would not just be large. It would potentially require some additional explanation beyond ordinary gravitational collapse. Whether that turns out to be a coincidental alignment of unrelated structures viewed from our particular vantage point, some kind of large-scale periodic pattern in the early universe that current models do not yet account for, or, most likely by far given the history of similar claims, a statistical effect that will look smaller or disappear entirely once independent teams re-examine the same region with different methods and larger datasets. It is worth being honest about why this pattern, an exciting discovery of an enormous structure followed by years of statistical scrutiny and partial walkback, keeps recurring throughout this part of the episode. The largest structures in the universe are, definitionally, rare. There are not many of them to study. The surveys capable of detecting them at these extreme distances are relatively young, and every method used to find them, redshift surveys, gamma-ray burst clustering, quasar absorption mapping, comes with its own specific statistical limitations that take years of follow-up work by independent research teams to fully understand. None of that means these discoveries are wrong, or that the astronomers making them are being careless. It means this particular frontier of astronomy, unlike the well-established structures from earlier chapters such as the Virgo Cluster or the local group, is still actively being tested, argued over and refined, and an honest account of it has to say so plainly, rather than presenting every headline-making structure as a settled fact. What makes all of this more than an academic argument over bragging rights is the theoretical stakes sitting underneath it. If a genuine structure several billion light-years across, whether the Hercules corona Borealis Great Wall, the Giant Arc, or the Big Ring, turns out to be real and confirmed, it does not just set a new record. It directly challenges one of the foundational assumptions built into essentially every modern cosmological model, an assumption so important that the next chapter is devoted to it entirely. Every calculation described so far in this episode, from Hubble's law relating redshift to distance, to the models cosmologists use to interpret the faint afterglow of the Big Bang, to the estimated age and expansion rate of the universe itself, rests on one foundational assumption, so basic that it is easy to overlook how much weight it is quietly carrying. That assumption is called the Cosmological Principle, and it makes two related claims: that the universe is homogeneous, meaning it has roughly the same average density of matter everywhere, and that it is isotropic, meaning it looks roughly the same in every direction you point a telescope. Crucially, the principle does not claim the universe looks uniform at every scale. Obviously, it does not. A single galaxy is far denser than the empty space between galaxies, and the difference between a cluster and a void is enormous. The cosmological principle instead claims that once you average over a large enough volume, a volume big enough to smooth out the lumps described in every chapter of this episode so far, the differences between one large region and another should essentially disappear. Zoom out far enough, the principle says, and the universe should start to look the same everywhere. This is not an assumption cosmologists adopted for convenience, though it certainly is convenient. It emerges most directly from measurements of the cosmic microwave background, the relic radiation left over from roughly 380,000 years after the Big Bang, when the universe first became transparent enough for light to travel freely. That radiation, mapped in extraordinary detail by satellites including COBE, WMAP and Planck across the past few decades, shows the early universe was remarkably smooth, varying in temperature by only about 1 part in 100,000 across the entire observable sky, the same tiny fluctuation described earlier as the seed pattern for all later structure. If the early universe was that smooth, and if gravity alone, acting the same way everywhere according to the same physical laws, is what grew those fluctuations into today's galaxies, clusters, and filaments, then on a large enough scale, the resulting structure should still average out to roughly the same density everywhere, even after billions of years of that gravitational growth. The cosmological principle is a claim that the universe's current lumpiness is a local, small-scale phenomenon layered on top of an underlying large-scale uniformity, rather than the underlying reality all the way up. Why does any of this matter enough to devote an entire chapter to it? Because the cosmological principle is not just a philosophical preference for a tidy universe. It is load-bearing, structural machinery inside the mathematics that describes cosmic expansion itself. The equations Einstein developed for general relativity, applied to the universe as a whole, become dramatically simpler and in practice solvable at all with our current tools if you assume homogeneity and isotropy from the start. The specific simplified solution built on that assumption, called the FLRW metric after the physicists Alexander Friedmann, Georges Lemaitre, Howard Robertson, and Arthur Walker, is the mathematical backbone underneath essentially every modern calculation of the universe's age, its expansion history, and its ultimate fate. If the actual universe turned out to be significantly less uniform on large scales than the cosmological principle assumes, if genuinely enormous structures, connected and physically real, kept appearing no matter how far out you looked, then some of that backbone mathematics would need serious revision, and conclusions drawn from it, including the universe's age of roughly 13.8 billion years and its currently accelerating expansion, would need to be re-examined for how sensitive they actually are to the uniformity assumption baked into their foundations. This is exactly why the structures from the previous several chapters generate genuine scientific caution among cosmologists, not just excitement. Every one of them, the Sloan Great Wall, the more contested Hercules Corona Borealis Great Wall, the Giant Arc, the Big Ring, is a candidate piece of evidence, however debated, that the universe might remain lumpy at scales larger than the cosmological principle comfortably allows. A single such structure, even if confirmed beyond doubt, would not by itself overturn modern cosmology. A genuinely representative universe can still contain rare, unusually large outliers, the way a genuinely fair set of dice can still occasionally roll the same number 10 times in a row. But if structures at these extreme scales turned out to be common, rather than rare statistical flukes, that would suggest the true scale at which the universe becomes smooth and uniform is considerably larger than current models assume. Or, in the most dramatic version of this concern, that the assumption of large-scale uniformity is wrong altogether and needs to be replaced with something more complicated. So cosmologists needed, and eventually built, a specific answer to a specific question. Exactly how large does a region of the universe need to be, on average, before it reliably smooths out into the kind of uniform density the cosmological principle predicts? That answer has a name coined from a phrase used informally by researchers analysing exactly this question, and it draws a hard theoretical line that every structure discussed in this episode gets measured against. The phrase end of greatness was coined informally by astronomers in the early 1990s, during the first wave of redshift surveys described several chapters ago, to describe a specific and, at the time, slightly surprising observation. As those early surveys mapped larger and larger volumes of the nearby universe, the structures they found, filaments, walls, voids, kept getting more impressively large for a while, culminating in discoveries like the CFFA2 Great Wall. But then something changed. Once survey volumes grew large enough, the largest structures found within them stopped scaling up proportionally. Instead, the universe started to look statistically similar no matter how much larger a volume you examine, once that volume passed a certain threshold size. The excitement of ever larger discoveries, in other words, had an end point, a scale beyond which the universe's lumpiness simply stopped compounding and started averaging out. Researchers called that transition the end of greatness, a slightly wry name for the discovery that biggest is not, in fact, unlimited. Pinning down the exact size of that transition scale, the point where the universe reliably becomes statistically uniform, took considerably more data than the original 1990s surveys provided. A particularly influential analysis, Published in 2005 by the astronomer David Hogg and colleagues using early Sloan Digital Sky Survey data, examined how the measured density of galaxies varied depending on the size of the region being averaged over. Small regions, unsurprisingly, showed enormous variation, some containing dense clusters, some containing near-empty voids. But as the team increased the size of the regions being compared, the variation in average density shrank steadily, and by the time regions reached roughly 260 to 370 million light-years across, the differences between regions had dropped to a level consistent with simple statistical noise, essentially confirming that beyond that scale, the universe really does behave the way the cosmological principle predicts, broadly uniform, once you are averaging over a large enough chunk of it. This homogeneity scale, sitting somewhere in the range of a few 100 million light-years, is where the tension with the largest claimed structures becomes concrete and quantifiable rather than a vague worry. The Sloan Great Wall, at roughly 37 billion light-years, is already 3 to 5 times larger than the scale at which the universe is supposed to have smoothed out into uniformity. The Hercules Corona Borealis Great Wall's original high-end estimate, at up to 10 billion light-years, and the Giant Arc, at 3.3 billion light-years, are further still beyond that boundary, by factors that get harder to explain the larger they get. None of these structures, on their own, technically violates the cosmological principle, because the principle is a statistical statement about averages across the whole universe, not a rule forbidding any individual large structure from existing. A genuinely fair universe governed by random density fluctuations, seeded the way the previous chapters described, will still occasionally produce an unusually large connected structure purely by chance. The same way a fair coin flipped enough times will eventually produce an improbably long streak of heads. The real theoretical concern is about how many such outsized structures the universe is producing, and how that count compares to what standard models actually predict. This is where large cosmological simulations, the same kind introduced earlier in the discussion of the cosmic web, earn their keep, because a simulation like the Millennium simulation starts from the same measured initial conditions as the real universe, seeded from the same kind of tiny density fluctuations recorded in the cosmic microwave background, and evolves them forward using the same understood laws of gravity. It can be used to predict how large the largest structures forming anywhere within a simulated volume the size of the observable universe should typically be, and how often something dramatically larger than that typical size should appear purely by chance. Running this kind of analysis, cosmologists have found that structures on the scale of the Sloan Great Wall, while unusually large, sit within the range that standard models predict should occasionally occur, rare but not impossible. Structures approaching the higher-end estimates for the Hercules Corona Borealis Great Wall or the Giant Arc, however, sit at the very edge of what standard models can comfortably accommodate, or, according to some published analyses, slightly beyond it, depending on exactly how the structure's boundary and connectivity are defined, which circles back directly to the measurement uncertainty problem described in earlier chapters. None of this amounts to a crisis in cosmology, at least not yet, and responsible researchers are careful to say so. It amounts to a genuinely open, actively worked research question sitting exactly at the edge of current knowledge. Are the largest structures ever claimed real, connected, physical objects that push right up against, or slightly past, what standard cosmological models predict should be possible, or are the most extreme claims artifacts of small samples and difficult statistics, structures that will shrink toward the safely predictable Sloan Great Wall scale once better data arrives? The honest answer, as of this episode, is that both possibilities remain on the table, and the way astronomers are working to settle the question says something important about how science actually makes progress on questions this large. Resolving the tension from the previous chapter, whether the largest claimed structures are real outliers permitted by standard cosmology or artifacts of thin, hard-to-interpret data, does not require a clever theoretical argument so much as it requires exactly what has resolved every previous scale-related surprise in this episode: more data, gathered more carefully, over a larger volume of sky. That work is well underway, and it is worth naming the specific instruments doing it, because they represent a genuine generational leap over the surveys described earlier. The Dark Energy Spectroscopic Instrument, known as DESI, began full operations in 2021, mounted on a telescope in Arizona, and is designed to measure redshifts, and therefore three-dimensional positions, for tens of millions of galaxies and quasars, an order of magnitude beyond even the Sloan Digital Sky Survey's already enormous catalogue. Its primary scientific goal is actually to measure the expansion history of the universe with extreme precision, refining our understanding of dark energy, the mysterious factor driving the universe's expansion to accelerate. But a byproduct of a survey this large and this precise is a correspondingly larger, better sampled map of the cosmic web, one with enough statistical power to test whether structures on the scale of the Sloan Great Wall, or larger, appear as often as standard models predict, or more often than they should. The European Space Agency's Euclid Space Telescope, launched in 2023, approaches the same underlying question from a different angle, using extremely precise imaging across roughly a third of the entire sky to map both the distribution of galaxies and a subtler effect called weak gravitational lensing, in which the light from distant galaxies is very slightly bent and distorted by the gravity of matter, including invisible dark matter, sitting between them and Earth. Because weak lensing is sensitive to all mass, not just the mass that happens to be shining as visible galaxies, it offers an independent check on where the universe's largest concentrations of matter actually sit, one that does not depend entirely on galaxy redshift measurements at all. The Vera Rubin Observatory, beginning its main sky survey in the mid-2020s from a mountaintop in Chile, adds yet another independent, extremely wide and extremely deep imaging dataset to the same effort. Astronomers already have one clear, well-documented example of what happens when a claimed record structure gets tested against a larger, more careful dataset, and it is worth walking through because it illustrates the pattern the field expects to see play out again with the more recent, more contested discoveries. Before the CFA2 Great Wall and Sloan Great Wall era, an earlier claimed superstructure identified in a much smaller and shallower 1980s survey was, for a brief period, treated as an unusually large discovery in its own right. Once larger surveys covering the same region of sky arrived, that earlier structure was found to be substantially smaller and less coherent than the initial small sample analysis had suggested, a real feature, but a far less extreme one. The lesson researchers draw from cases like this, and it is a lesson repeated explicitly in papers discussing the Hercules Corona Borealis Great Wall, the Giant Arc and the Big Ring, is that first detections of extreme structures built on small samples systematically tend to shrink, not grow, once independently verified with larger datasets. That does not guarantee the newer, still contested structures will shrink the same way. It does mean that shrinkage, rather than confirmation at face value, is the historically more common outcome, and it is the reason careful astronomers describe these structures with hedged language rather than treating headline-size estimates as settled fact. There is also a specific alternative explanation astronomers actively test for whenever an enormous structure turns up, called a projection effect, and it is worth explaining plainly because it is genuinely subtle. When you observe a large volume of sky and estimate distances using redshift, or especially using less direct methods like gamma-ray burst clustering or quasar absorption mapping, measurement uncertainty means that objects at somewhat different true distances can appear to fall within the same distance bracket in your data. If 2, 3, or more genuinely separate, unconnected clusters or filaments happen to sit along roughly the same line of sight from Earth, at distances close enough that measurement uncertainty blurs them together, they can appear in the data as one single, enormous connected structure, when in physical reality they are several smaller, entirely unrelated structures merely lined up by chance from our particular vantage point in the universe. Distinguishing a genuine, physically connected superstructure from a projection effect artifact requires either much more precise distance measurements, capable of resolving the difference between structures that are truly at the same distance versus merely appearing to be, or entirely independent confirmation, using a second detection method that would be unlikely to produce the exact same false alignment by coincidence. This is precisely the kind of test the next generation of surveys, DESI, Euclid, and the Vera Rubin Observatory among them, is built to run at a scale no previous survey could manage, and the results, still arriving as this episode is written, will very likely settle at least some of the open questions from the previous 3 chapters within the coming decade. Whatever the final verdict turns out to be for any individual contested structure, the deeper answer this whole hunt is really chasing sits one level below the size of any single wall or arc. What is actually building these structures in the first place? And why does the universe organize itself into filaments and voids at all, rather than some other pattern entirely? Every structure covered in this episode, from the modest local group to the still disputed giant arc, owes its shape to a substance that has never been directly detected, has no confirmed particle identity, and is currently understood almost entirely through the gravitational footprints it leaves behind: dark matter. It was introduced earlier in this episode through Fritz Zwicky's 1930s cluster measurements and through the puzzle of galaxy rotation speeds, but its role in building the cosmic web itself deserves its own explanation, because without it, the filaments, walls and voids described across the last several chapters would likely not exist in anything like their current form, and might not have had time to form at all. The key property that makes dark matter such an effective architect is what it does not do. It does not interact with light, or with the electromagnetic force generally at all. Ordinary matter, the atoms making up stars, planets and people, interact strongly with light and with other ordinary matter, and in the early universe, before the moment called recombination, roughly 380,000 years after the Big Bang, ordinary matter was locked in a hot, dense plasma, tightly coupled to photons, radiation that constantly pushed back against any attempt by gravity to clump that matter together. Dark matter felt no such resistance. Unaffected by radiation pressure, it began collapsing under gravity's pull almost immediately after inflation ended, forming an early scaffold of dense clumps and connecting filaments long before ordinary matter was free to do the same. When recombination finally arrived and photons decoupled from ordinary matter, releasing the light we now observe as the cosmic microwave background, ordinary matter was suddenly free to fall gravitationally too, and it fell overwhelmingly toward the scaffold dark matter had already built. Gas collected along dark matter's pre-existing filaments and pooled in its pre-existing halos, eventually cooling and compressing enough to ignite the first stars and galaxies precisely along the threads that dark matter had already laid down. This scaffolding explanation is not a hypothesis invented after the fact to fit inconvenient observations. It is a direct, quantitative prediction, and it is the reason the cosmological simulations described in earlier chapters, the Millennium simulation among them, work as well as they do. Those simulations track dark matter's gravitational collapse in extraordinary detail and separately model how ordinary gas would be expected to fall into and light up the resulting scaffold, and when the two are combined, the simulated result reproduces the real cosmic webs, filaments, walls and voids with a precision that would be difficult to explain as coincidence. Roughly 85% of all the matter in the universe, by current best estimates, is dark matter rather than ordinary matter, which means the cosmic web observed through galaxy light is, in an important sense, only the illuminated fraction of a far larger invisible structure, one built predominantly out of a substance we still cannot directly see, name or, so far, detect in any laboratory on Earth. Dark matter explains how the web was built. A second, entirely different mystery substance explains what is now, slowly, tearing that same web apart, and it goes by the equally provisional name dark energy. In 1998, two independent research teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rias, measuring the brightness of a specific type of exploding star called a Type Ia supernova across a wide range of cosmic distances, found something no one had expected. The universe's expansion is not slowing down under gravity's pull, the way essentially every cosmologist at the time assumed it should be. It is speeding up. The three researchers shared the 2011 Nobel Prize in Physics for the discovery, and the explanation currently favoured by cosmologists is that some form of energy, permeating all of space itself and exerting a kind of negative pressure, is pushing space apart faster than gravity can pull matter together, an effect that becomes more dominant the larger the distances involved, because gravity's pull weakens with distance, while dark energy's outward push does not. That accelerating expansion has a direct, sobering consequence for the largest structures described across this entire episode. Gravity built the cosmic web over roughly 13 billion years, slowly amplifying tiny density fluctuations into galaxies, clusters, superclusters, and the Great Walls debated in earlier chapters. But dark energy is now winning the tug-of-war at the very largest scales, stretching space apart faster than gravity across those distances can pull it back together. Structures on the scale of an individual galaxy, or even a cluster like Virgo, remain gravitationally bound and will not be torn apart. Their internal gravity is simply too strong for dark energy's effect at that comparatively small scale to overcome. But the connections between separate clusters and superclusters, the very filaments that define the cosmic web's structure, are, on the longest timescales, being gradually stretched thinner, and eventually many of them are expected to stretch until they effectively disconnect entirely. This means the largest structures observed today, the Sloan Great Wall, and, if confirmed, its more extreme contested rivals, may represent something close to a ceiling, not because gravity has run out of time to build something larger, but because the accelerating expansion described in this chapter is increasingly working against exactly the kind of large-scale gravitational assembly that built them in the first place. The universe, in other words, may be entering an era in which the great walls it has already built are the largest it will ever manage to build again. Return for a moment to the very first image of this episode, a single pale point of light, indistinguishable from thousands of others. That happens to be our Sun. Every chapter since has been, in a sense, an exercise in discovering exactly how accurate and exactly how limited that image really is. The Sun is one star among the 100 billion or more crowding the Milky Way's spiral arms. The Milky Way is one galaxy among the 54 or so crammed into the local group, itself a gravitational grain of sand held at arm's length against the far larger Virgo Cluster, itself only a regional hub within the 100,000 galaxy basin of Laniakea, itself apparently only one connected thread among the filaments, walls, and voids of the cosmic web, a structure whose single largest confirmed component, the Sloan Great Wall, stretches 1.37 billion light-years, and whose most extreme disputed candidates, the Hercules Borealis Great Wall, the giant arc, the Big Ring, may stretch several times that far again if they hold up under the more precise surveys now underway. Layered on top of every single one of those structures is the web of glowing threads and dark voids described a few chapters back, built first from dark matter's early, radiation-proof head start on gravitational collapse, then decorated with the visible galaxies that light up its brightest filaments and cluster at its densest nodes, all of it seeded from density variations of roughly 1 part in 100,000, recorded in the faint afterglow of a universe less than 400,000 years old. And now at the largest scales this episode has covered, that same web is slowly being pulled apart again, not by any flaw in how it was built, but by dark energy's steady, still not fully understood push, stretching the space between filaments a little further apart with every passing year, working against exactly the gravitational assembly that took 13 billion years to build in the first place. It would be tidy to end this episode with a confident, singular answer to the question in its title, a clean statement of exactly which structure holds the record for largest in the universe. The honest answer laid out across the last several chapters is that the record is genuinely contested and likely to keep changing as better instruments come online. The Sloan Great Wall is the largest structure confirmed with the kind of statistical confidence that comes from mapping hundreds of thousands of individual galaxy positions directly. The Hercules Borealis Great Wall, the giant arc, and the Big Ring may be considerably larger still, or they may shrink toward more modest, less record-breaking sizes once the dark energy spectroscopic instrument Euclid and the Vera Rubin Observatory finish mapping the same regions of sky with far greater precision than any previous survey could manage. Either outcome would be a real scientific result, not a disappointment. Astronomy has never actually promised final answers on a fixed schedule. It has only promised that the answers get more reliable, one better dataset at a time, and that promise has held without exception at every single step of the climb this episode has traced, from the first parallax measurement of a star's distance in 1838 to the still-running surveys of today. There is a specific kind of vertigo built into everything this episode has described, and it is worth naming directly rather than smoothing over. A structure like the Sloan Great Wall, 1.37 billion light-years long, is so large that no single observer, no single instrument, no single human lifetime could ever traverse it, or see it whole from any vantage point actually available to us. We know it exists, and we know roughly its shape and size, entirely through indirect reconstruction, measuring tiny shifts in the light of individual galaxies, one at a time, across years of careful observation, and assembling those millions of individual measurements into a three-dimensional map that no living creature has ever seen with its own eyes and never will. That is, when you sit with it, a genuinely strange kind of achievement, a species confined entirely to one small rocky planet, orbiting one ordinary star in one unremarkable spiral arm, has managed to measure the shape of structures a billion light-years across, using nothing but light that left its source before that same rocky planet had finished forming. That, in the end, is the actual answer this episode has to offer, and it is a more honest one than any single number could be. The universe's largest structures are, almost by definition, larger than any framework built for measuring modestly sized things can comfortably handle, which is exactly why every chapter of this climb, from group to cluster to supercluster, to the still disputed edges of the cosmic web, has involved building a new tool, a new survey, a new statistical method, precisely because the old one had run out of room. That process is not finished, and there is no reason to think it ever will be, not because the universe keeps getting bigger, but because our capacity to measure it keeps getting better, and every improvement in that capacity has, so far, revealed something larger than we previously knew how to look for. We began this episode as a single pale point of light. We end it as, so far as we know, the only point of light that has ever managed to measure the whole web it belongs to. So, how big is the largest structure in the universe? The most defensible answer, built from confirmed galaxy surveys rather than contested statistical claims, is the Sloan Great Wall, a connected filament of galaxies roughly 1.37 billion light-years long, discovered in 2003, and still, on the strength of the evidence, the largest structure astronomers can confirm with real confidence. Beyond it sit several larger candidates: the Hercules Corona Borealis Great Wall, the Giant Arc, the Big Ring, each detected through newer and less thoroughly tested methods, each still working through the years of independent scrutiny that eventually settled every earlier claim in this episode's history. That uncertainty is not a weakness in the story. It is the story. 100-year climb, one better survey at a time, from a solar system we once thought was the whole universe, to a cosmic web whose largest threads may still be waiting to be confirmed or quietly ruled out by instruments now gathering their first data. Somewhere in that web, riding one ordinary spiral arm, circling one unremarkable star, is the only vantage point from which any of this has ever been measured. That, more than any single number, is the actual scale of what has been accomplished here.